Clipping. In this video, we are going to see about clipping. Clipping is a process to cut off the part of the image which is outside the window. For any object or image, there could be three possibilities. First, the entire image is within the window and therefore the entire image will be displayed within the viewport. Second, the entire image is outside the selection area, that is window, and therefore the complete image will be ignored and will not be. Finally, the third possibility is an image of which a part is inside the selection area and the other part is outside. The selection of the part of the image which is inside the window is done by some algorithm. Different algorithms are available for different kinds of. The following is a list of clipping algorithms: point clipping algorithm, line clipping algorithm, polygon clipping algorithm. Point clipping. In this video, we are going to see about point clipping. Assuming that the clip window is a rectangle in standard position, we save a point P is equal to x, y for display if the following inequalities are satisfied. Where the edges of the clip window, that is xw minimum, xw maximum, yw minimum, yw maximum, can be either the world coordinate window boundaries or viewport boundaries. If any one of these four inequalities is not satisfied, the point is clipped, that is not saved for display. xw minimum lesser than or equal to x lesser than or equal to xw maximum. Yw minimum lesser than or equal to y lesser than or equal to yw maximum. Although point clipping is applied less often than line or polygon clipping, some applications may require a point clipping procedure. For example, point clipping can be applied to scenes involving explosions or sea foam that are modeled with particles, that is, points distributed in some region of the scene. Line clipping. In this video, we are going to see about line clipping. A line clipping procedure involves several parts. Figure illustrates possible relationships between line positions and a standard rectangular clipping region. First, we can test a given line segment to determine whether it lies completely inside the clipping window. If it does not, we try to determine whether it lies completely outside the window. Finally, if we cannot identify a line as completely inside or completely outside, we must perform intersection calculations with one or more clipping boundaries. We process lines through the inside-outside test by checking the line endpoints. A line with both endpoints inside all clipping boundaries, such as the line from P1 to P2, is saved. A line with both endpoints outside any one of the clip boundaries, that is line P3 to P4, that is line P3 P4 is outside the window. All other lines cross one or more clipping boundaries and may require calculation of multiple intersection points. To minimize calculations, we try to devise clipping algorithms that can efficiently identify outside lines and reduce intersection calculations. For a line segment with endpoints, that is x1, y1 and x2, y2, and one or both endpoints outside the clipping rectangle, the parametric representation could be used to determine values of parameter u for intersections with the clipping boundary coordinates. X is equal to x1 plus u into x2 minus x1. Y is equal to y1 plus u into y2 minus y1. 0 lesser than or equal to u lesser than or equal to 1. If the value of u for an intersection with the rectangle boundary edge is outside the range 0 to 1, the line does not enter the interior of the window at that boundary. If the value of u is within the range from 0 to 1, the line segment does indeed cross into the dipping area. This method can be applied to each clipping boundary edge in turn to determine whether any part of the line segment is to be displayed. Line segments that are parallel to window edges can be handled as special cases. Clipping line segment with these parametric tests requires a good deal of computation, and faster approaches to clipping are possible. Some algorithms are designed explicitly for two-dimensional pictures, and some are easily adapted to three-dimensional applications. Polygon clipping. In this video, we are going to see about polygon clipping. Convex polygonal clipping window. A polygon is called a convex if the line joining any two interior points of the polygon lies completely inside the polygon. A non-convex polygon is said to be concave. To clip polygons, we need to modify the line clipping procedures. A polygon boundary processed with a line clipper may be displayed as a series of unconnected line segments. Depending on the orientation of the polygon to the clipping window, what we really want to display is the bounded area after clipping. For polygon clipping, we require an algorithm that will generate one or more closed areas that are then scan converted for the appropriate area fill. The output of a polygon clipper should be a sequence of vertices that defines the clipped polygon boundaries. Sutherland-Hodgman polygon clipping. A polygon can be correctly clipped by processing a polygon boundary as a whole against each window edge. This can be accomplished by processing all polygon vertices against each clipped rectangle boundary in turn. We can begin with the initial set of polygon vertices. We could first clip the polygon against the left rectangle boundary to vertices. The new set of vertices could then be successively passed to a right boundary clipper, a bottom boundary clipper, at every step, a new sequence of output vertices is generated and passed to the next window boundary clipper. We clip each edge of the polygon in turn against the edge of the window boundary clipper, forming a new polygon whose vertices is determined as follows. If the first vertex is outside the window boundary and the second vertex is inside, both the intersection point of the polygon edge with the window boundary and the second vertex are added to the output vertex list. If both the input vertices are inside the window boundary, only second vertex is added to the output vertex list. If the first vertex is inside the window boundary and the second vertex is outside, only edge intersection with the window boundary is added to the output vertex list. If both input vertices are outside the window boundary, nothing is added to the output list. Once all the vertices have been processed for one clipped window boundary, the output list of vertices is clipped against the next window boundary. Special attention is necessary in using the Sutherland-Hodgman algorithm in order to avoid unwanted effects. For example, the correct result should consist of two disconnected parts, a square in the lower left corner of the clipping window and a triangle at the top. However, the algorithm produces a list of vertices that forms a figure with the two parts connected by extra edges. So convex polygons are correctly clipped by this algorithm, but concave polygons may be displayed with extraneous lines. This occurs when the clipped polygon should have two or more separate sections. But since there is only one output vertex list, the last vertex in the list is always joined to the first vertex. Coherence-Sutherland line clipping. In this video, we are going to see about Coherence-Sutherland line clipping. This is one of the oldest and most popular line clipping procedures. Generally, the method speeds up the processing of line segments by performing initial tests that reduce the number of intersections that must be calculated. Every line endpoint in a picture is assigned a 4-digit binary code called a region code that identifies the location of the point relative to the boundaries of the clipping rectangle. Regions are set up in reference to the boundaries. Each bit position in the region code is used to indicate one of the 4 relative coordinate positions of the point with respect to the clip window to the left, right, top, or bottom. By numbering the bit positions in the region code as 1 through 4 from right to left, the coordinate regions can be correlated with the bit positions as bit 1 left, bit 2 right, bit 3 below, bit 4 above. A value of 1 in any bit position indicates that the point is in the relative position, otherwise the bit position is set to 0. If a point is within the clipping rectangle, the region code is 0000. A point that is below and to the left of the rectangle has a region code of 0101. Bit values in the region code are determined by comparing endpoint coordinate values, that is x, y, to the clip boundaries. Bit 1 is set to 1 if x lesser than xw minimum. The other 3 bit values can be determined using similar comparisons. For languages in which bit manipulation is possible, region code bit values can be determined with the following 2 steps. Calculate differences between endpoint coordinate and clipping boundaries. Use the resultant sign bit of each difference calculation to set the corresponding value in the region code. Bit 1 is a sign bit of x to xw minimum. Bit 2 is a sign bit of xw maximum to x. Bit 3 is a sign bit of y to yw minimum, and bit 4 is a sign bit of yw maximum to y. Once we have established region codes for all line endpoints, we can quickly determine which lines are completely inside the clip window and which are clearly outside. Any lines that are completely contained within the window boundaries have a region code of 0000 for both endpoints, and we trivially accept these lines. Any lines that have a 1 in the same bit position in the region codes for each endpoint are completely outside the clipping rectangle, and we trivially reject these lines. We would discard the line that has a region code of 1001 for one endpoint and a code of 0101 for the other endpoint. Both endpoints of this line are left of the clipping rectangle as indicated by the 1 in the first bit position of each region code. A method that can be used to test lines for total clipping is to perform the logical and operation with both region codes. If the result is not 0000, the line is completely outside the clipping region. Lines that cannot be identified as completely inside or completely outside a clip window by these tests are checked for intersection with the window boundaries. We begin the clipping process for a line by comparing an outside endpoint to a clipping boundary to determine how much of the line can be discarded. Then the remaining part of the line is checked against the other boundaries, and we continue until either the line is totally discarded or a section is found inside the window. We set up our algorithm to check line endpoints against clipping boundaries in the order left, right, bottom, top. Starting with the bottom endpoint of the line from P1 to P2, we check P1 against the left, right and bottom boundaries in turn and find that this point is below the clipping rectangle. We then find the intersection point P1' with the bottom boundary and discard the line section from P1 to P1'. The line now has been reduced to the section from P1' to P2. Since P2 is outside the clip window, we check this endpoint against the boundaries and find that it is to the left of the window. Intersection point P2' is calculated, but this point is above the window. So the final intersection calculation yields P2' and the line from P1' to P2' is saved. This completes processing of this line, so we save this part and go on to the next line. Point P3 in the next line is to the left of the clipping rectangle, so we determine the intersection P3' and eliminate the line section from P3 to P3'. By checking region codes for the line section from P3' to P4, we find that the remainder of the line is below the clip window and can also be discarded. Intersection points with the clipping boundary can be calculated using the slope-intercept form of the line equation. For a line with endpoint coordinates, that is x1, y1 and x2, y2, their coordinate of the intersection point with the vertical boundary can be obtained by the calculation y is equal to y1 plus m into x minus x1, where the x value is set either to xw minimum or to xw maximum, and the slope of the line is calculated as m is equal to y2 minus y1 by x2 minus x1. Similarly, if we are looking for the intersection with the horizontal boundary, the x-coordinate can be calculated as with y set either to yw minimum or to yw maximum. Midpoint subdivision algorithm. In this video, we are going to see about midpoint subdivision algorithm. Midpoint subdivision is a clipping algorithm that follows a divide and conquer strategy. We have seen that the Cohen-Sutherland subdivision line clipping algorithm requires the calculation of the intersection of the line with the window edge. These calculations can be avoided by repetitively subdividing the line at its midpoint. Like previous algorithm, initially the line is tested for visibility. If the line is completely visible, it is drawn, and if it is completely invisible, it is rejected. If line is partially visible, Then it is subdivided into two equal parts. The visibility tests are then applied to each half. This subdivision process is repeated until we get completely visible and completely invisible line segments. Line P1, P2 is partially visible. It is subdivided into two equal parts, P1, P3 and P3, P2. Both the line segments are tested for visibility and found to be partially visible. Both line segments are then subdivided into two equal parts to get midpoints P4 and P5. It is observed that line segments P1, P4 and P5, P2 are completely invisible and hence rejected. However, the line segment P3, P5 is completely visible and hence drawn. The remaining line segment P4, P3 is still partially visible. It is then subdivided to get midpoint P6. It is observed that P6, P3 is completely visible whereas P4, P6 is partially visible. Thus, P6, P3 line segment is drawn and P4, P6 line segment is further subdivided into equal parts to get midpoint P7. Now it is observed that line segment P4, P7 is completely invisible and line segment P7, P6 is completely visible, and there is no further partially visible segment. Midpoint subdivision algorithm. Read two endpoints of the line, say P1 into x1, y1 and P2 into x2, y2. Read two corners, left top and right bottom of the window, say wx1, wy1 and wx2, wy2. Assign region codes for two endpoints using the following steps. Initialize code with bits 0000. Set bit 1 if x lesser than wx1. Set bit 2 if x greater than wx2. Set bit 3 if y lesser than wy1. Set bit 4 if y greater than wy2. Check for visibility of line. If region codes for both endpoints are 0, then the line is completely visible. Hence, draw the line and go to step 6. If region codes for endpoints are not 0 and the logical ANDing of them is also non-zero, then the line is completely invisible, so reject the line and go to step 6. If region codes for two endpoints do not satisfy the conditions in the above points, the line is partially visible. Divide the partially visible line segment in equal parts and repeat step 3 through 5 for both subdivided line segments until you get completely visible and completely invisible line segments. Stop. Filling. In this video, we are going to see about filling. In the raster graphic system, we can display regions filled with colors. Here, color is an integer pointing to any entry of the color lookup table or a color palette. Polygon filling is a process of coloring the area of a polygon. area may be thus defined at the pixel or geometrical level. We can describe the area as the total number of pixels it contains by the bounding pixels that outline the polygon. The polygon defined by the total number of pixels is called as interior. Here we want to develop scan conversion algorithm that generate all pixels in the interior of a polygon. There are two general classes of polygon filling algorithms. Fill algorithms that spread out from a seed. Scanline algorithms which fill a polygon one scan line at a time. The seed fill algorithm is also called flood fill algorithm. As you plant a seed, the pixel where you start, and recursively more and more seeds are planted around the original seed. The purpose is to color an entire area of connected pixels with the same color. Each new seed is responsible for coloring the pixel at its position and testing for new pixels around it that have to be colored. Flood fill algorithm. In this video, we are going to see about flood fill algorithm. In this method, we start from the given interior, that is, initial pixel called as seed. From this seed, the algorithm inspects all of the surrounding 8 pixels to see whether the boundary extent is reached. This process is repeated till all of the interior pixels are inspected. Then, our algorithm inspects all 8 points surrounding the seed. If these points are not on the boundary, each will be filled. Now each of these points becomes the seed. The algorithm continues to work in this fashion until all points surrounding all seeds enter into the border. Please understand that this method is used to fill the area bounded by different color boundaries. Such an area can be replacing a specified interior color instead of reaching for a boundary color value. The procedure is very simple as follows. Choose random interior points. Replace the interior color with the desired color. If area to be painted has more than one color, then reassign all the pixel values to the same colors. Repeat the process until all interior points have been repainted. Using either 4 connected or 8 connected approach, we then step through the pixel positions until all interior points have been repainted. The algorithm is the simplest one for solid polygon filling, but it is very slow as each and every pixel inside the polygon is tested for coloring. This algorithm looks for interior color, which is to be replaced as a boundary color. Please note, for large polygons, this algorithm may fail because it requires a frame buffer free of pixels with a polygon interior style, and another reason is that it requires a seed pixel that has more knowledge about the polygon shape, which is very tedious. We have two approaches here, namely recursive approach, stack-based approach. recursive approach. In this video, we are going to see about recursive approach. Using recursion is not safe as recursions may cause stack overflow when larger areas are filled using this method. We now write recursive algorithm for 4 connected and 8 connected approaches. Algorithm 1. Recursive flood fill algorithm using 4 connected method. Void flood fill of int x, int y, int fill, int old underscore color. If get pixel of x, y is equal to old underscore color. Set color of fill. Set pixel of x, y. Flood fill of x plus 1, y, fill, old underscore color. Flood fill of x minus 1, y, fill, old underscore color. Flood fill of x, y plus 1, fill, old underscore color. Flood fill of x, y minus 1, fill, old underscore color. Algorithm 2. Recursive flood fill algorithm using 8 connected method. Void flood fill of int x, int y, int fill, int old underscore color. If get pixel of x, y is equal to old underscore color. Set color of fill. Set pixel of x, y. Flood fill of x plus 1, y, fill, old underscore color. Flood fill of x minus 1, y, fill, old underscore color. Flood fill of x, y plus 1, fill, old underscore color. Flood fill of x, y minus 1, fill, old underscore color. Flood fill of x plus 1, y plus 1, fill, old underscore color. Flood fill x minus 1, y minus 1, fill, old underscore color. Flood fill of x minus 1, y plus 1, fill, old underscore color. Flood fill of x plus 1, y minus 1, fill, old underscore color. Stack-based approach. In this video, we are going to see about stack-based approach. We write a stack-based flood fill algorithm using 4 connected and 8 connected fill method. In this approach, we stack only the beginning positions for those pixels that have the value of old color. This algorithm does the same as we did with our recursive method, except that it uses a while loop that loops until the stack is empty. We push new positions onto the stack instead of calling it recursively again and again. Please note that the stack here is user defined, so we can control the stack size and willingly terminate the algorithm if stacks overflows. Algorithm 1. Stack-based flood fill algorithm using 4 connected fill method. Void flood fill of int x, int y, int new underscore color, int old underscore color. If of new underscore color is equal to old underscore color. Return empty stack open close bracket. If not a push of x, y. Return while of pop into x, y. Screen buffer x, y is equal to new underscore color. If x plus 1 lesser than w and screen buffer x plus 1 into y is equal to old underscore color. If not a push of x plus 1, y. Return if x minus 1 lesser than 0 and screen buffer x minus 1 into y is equal to old underscore color. If not a push of x minus 1, y. Return if y plus 1 lesser than w and screen buffer x into y plus 1 is equal to old underscore color. If not a push of x, y plus 1. Return if y minus 1 greater than or equal to 0 and screen buffer x into y minus 1 is equal to old underscore color. If not a push of x, y minus 1. Return Algorithm 2 stack based flood fill algorithm using 8 connected fill method. Void flood fill of int x, int y, int new underscore color, int old underscore color. If of new underscore color is equal to old underscore color. Return empty stack open close bracket. If not a push of x, y. Return while of pop into x, y. Screen buffer x, y is equal to new underscore color. If x plus 1 lesser than w and screen buffer x plus 1 into y is equal to old underscore color. If not a push of x plus 1, y. Return if x minus 1 lesser than 0 and screen buffer x minus 1 into y is equal to old underscore color. If not a push of x minus 1, y. Return if y plus 1 lesser than w and screen buffer x into y plus 1 is equal to old underscore color. If not a push of x, y plus 1. Return if y minus 1 greater than or equal to 0 and screen buffer x into y minus 1 is equal to old underscore color. If not a push of x, y minus 1. Return if x plus 1 lesser than w and screen buffer x plus 1 into y plus 1 is equal to old underscore color. If not a push of x plus 1, y plus 1. Return if x minus 1 lesser than 0 and screen buffer x minus 1 into y minus 1 is equal to old underscore color. If not a push of x minus 1, y minus 1. Return if y plus 1 lesser than w and screen buffer x minus 1 into y plus 1 is equal to old underscore color. If not a push of x minus 1, y plus 1. return. If y minus 1 greater than or equal to 0 and screen buffer x plus 1 into y minus 1 is equal to old underscore color. If not a push of x plus 1 comma y minus 1, return. Boundary fill algorithm. In this video, we are going to see about boundary fill algorithm. Another approach to area filling is to start at a point inside a region and paint the interior outward towards the boundary. If the boundary is specified in a single color, the fill algorithm proceeds outward pixel by pixel until the boundary color is encountered. This method, called the boundary fill algorithm, is particularly useful in interactive painting packages, where interior points are easily selected. In this algorithm, an area filling starts from a random point called as a seed inside a region, a continuous painting towards the boundary. Please understand that if the boundary is a monocolor, then the fill algorithm proceeds outwards pixel by pixel until the boundary color is encountered. Actually, there are two methods for proceeding to the neighboring pixels from the seed point. 4 adjacent point may be tested, 8 adjacent point may be tested. The algorithm is as followed. Step 1. Consider a random point that is seed. Step 2. In case of 4 connected, each pixel to the left, right, above and below are tested. If 8 connected, then the diagonal pixels are also tested. Step 3. Repeat this process until all pixels up to the boundary color for the area have been tested, that is, when boundary color is 8. There are two approaches here: recursive approaches, stack-based approaches. Recursive approach. In this video, we are going to see about recursive approach. We write two recursive algorithms here, one for 4 connected and one for 8 connected. In these procedures, the fill color is specified by fill and the boundary color is specified by boundary. Algorithm 1. Recursive boundary fill algorithm using 4 connected fill method. Void boundary fill of int x, int y, int fill, int boundary. Int current is equal to get pixel of x, y. If current not equal to boundary and current not equal to fill. Set color, that is fill. Set pixel x, y. Boundary fill of x plus 1, y, fill, boundary. Boundary fill of x minus 1, y, fill, boundary. Boundary fill of x, y plus 1, fill, boundary. Boundary fill of x, y minus 1, fill, boundary. This is a recursive algorithm that designs with a starting pixel called a seed inside a region and continuous painting towards the boundary. The algorithm checks to see if this pixel is a boundary pixel or has already filled. If answer is no, it fills the pixel and makes a recursive call to itself using each and every neighboring pixel as a new seed. If the answer is yes, the algorithm simply returns to its caller. A boundary fill procedure accepts as input the coordinates of an interior point x, y, a fill color and a boundary color. Starting from x, y, the procedure tests neighboring positions to determine whether they are of the boundary color. If not, they are painted with the fill color and their neighbors are tested. This process continues until all pixels up to the boundary color for the area have been tested. There may be two methods for proceeding to neighboring pixels from the seed point. Please note that these algorithms may not fill regions correctly if some interior pixels are already displayed in the fill color. This occurs because the algorithm checks next pixels both for boundary color and for fill color. Also note that encountering a pixel with the fill color can cause a recursive branch to terminate, leaving other interior pixels unfilled. To avoid this, we can first change the color of any interior pixels that are initially set to the fill color before applying the boundary fill procedure. Algorithm 2. Recursive boundary fill algorithm using 8 connected fill method. Read seed pixel of x, y, fill, boundary. Procedure boundary fill of x, y, fill, boundary. If get pixel of x, y less than or greater than fill and get pixel of x, y less than or greater than boundary, then set pixel x, y, fill. Boundary fill of x plus 1, y, fill, boundary. Boundary fill of x minus 1, y, fill, boundary. Boundary fill of x, y plus 1, fill, boundary. Boundary fill of x, y minus 1, fill, boundary. Boundary fill of x plus 1, y plus 1, fill, boundary. Boundary fill of x minus 1, y minus 1, fill, boundary. Boundary fill of x minus 1, y minus 1, fill, boundary. Boundary fill of x plus 1, y minus 1, fill, boundary. Stack-based approach. In this video, we are going to see about stack-based approach. We write a stack-based boundary fill algorithm using 4 connected fill method. Again, in this procedure also, the fill color is specified by fill and the boundary color is specified by boundary. In this method, horizontal pixels are considered across Scanline instead of 4 connected or 8 connected adjacent pixels. Then we need only stack with the beginning position for each horizontal pixel in Scanline instead of stacking all adjacent points around the seed. So now all Scanlines present in the polygon are considered respectively for filling the bounded area by the single color boundary. Let us write its algorithm now. Algorithm algorithm, stack-based boundary fill algorithm using 4 connected fill method. Read seed pixel of x, y, fill, boundary. Push pixel of x, y. While of stack lesser than or greater than empty. Pop pixel of x, y. Set pixel of x, y, fill. If get pixel of x plus 1, y lesser than or greater than fill and get pixel of x plus y lesser than or greater than boundary. Push pixel of x plus 1, y. If get pixel of x minus 1, y lesser than or greater than fill and get pixel of x minus 1, y lesser than or greater than boundary. Push pixel of x minus 1, y. If get pixel of x, y plus 1 lesser than or greater than fill and get pixel of x, y plus 1 lesser than or greater than boundary. Push pixel of x, y plus 1. If get pixel of x, y minus 1 lesser than or greater than fill and get pixel of x, y minus 1 lesser than or greater than boundary. Push pixel of x, y minus 1. End while. Scanline polygon fill algorithm. In this video, we are going to see about Scanline polygon fill algorithm. Recursive algorithms for seed fill methods have got 2 difficulties. The first difficulty is that if some inside pixels are already displayed in fill color, then recursive branch terminates, leaving further internal pixels unfilled. To avoid this difficulty, we have to first change the color of any internal pixels that are initially set to fill color before applying the seed fill procedures. Another difficulty with recursive seed fill methods is that it cannot be used for large polygons. This is because recursive seed fill procedures require stacking of neighboring points, and in case of large polygon, stacked space may be insufficient for stacking of neighboring points. To avoid this problem, more efficient method can be used. Such method fills horizontal pixel spans across scan lines instead of proceeding to 4 connected or 8 connected neighboring points. This is achieved by identifying the rightmost and leftmost pixels of the seed pixel and then drawing a horizontal line between these 2 boundary pixels. This procedure is repeated with changing the seed pixel above and below the line just drawn until the complete polygon is filled. With this efficient method, we have to stack only a beginning position for each horizontal pixel span instead of stacking all unprocessed neighboring positions around the current position. The scanline algorithm for filling of polygon. For each scan line crossing a polygon, this algorithm locates the intersection points of the scan line with the polygon edges. These intersection points are then sorted from left to right, and the corresponding positions between each intersection pair are set to the specified fill color. there are two stretches of interior pixels from x is equal to 6 to x is equal to 9 and x is equal to 12 to x is equal to 15. The Scanline algorithm first finds the largest and smallest y values of the polygon. It then starts with the largest y value and works its way down, scanning from left to right in the manner of a raster display. The important task in the Scanline algorithm is to find the intersection points of the scanline with the polygon boundary. When intersection points are even, they are sorted from left to right, paired, and pixels between paired points are set to the fill color, but in some cases intersection point is a vertex. When the scanline intersects polygon vertex, a special handling is required to find the exact intersection points. To handle such cases, we must look at the other endpoints of the two line segments of the polygon which meet at this vertex. If these points lie on the same side of the scanline, then the point in question counts as an even number of intersections. If they lie on opposite sides of the scanline, then the point is counted as single intersection. For scanline 1, the other endpoints B and D of the two line segments of the polygon lie on the same side of the scanline. Hence, there are two intersections resulting two pairs, 1 to 2 and 3 to 4. Intersections points 2 and 3 are actually same points. For scanline 2, the other endpoints D and F of the line segments of the polygon lie on the opposite sides of the scanline. Hence, there is a single intersection resulting two pairs, 1 to 2 and 3 to 4. For scanline 3, two vertices are the intersection points. For vertex F, the other endpoints E and G of the two line segments of the polygon lie on the same side of the scanline, whereas for vertex H, the other endpoints G and I of the two line segments of the polygon lie on the opposite side of the scanline. Therefore, at vertex F, there are two intersections and at vertex H, there is only one intersection. This results two pairs, 1 to 2 and 3 to 4, and points 2 and 3 are actually same points. We have seen that it is necessary to calculate x intersection points for scanline with every polygon side. We can simplify these calculations by using coherence properties. A coherence property of a scene is a property of a scene by which we relate one part of a scene with the other parts of a scene. Here, we can use a slope of an edge as a coherence property. By using this property, we can determine the x intersection value on the lower scan line if the x intersection value for current scan line is known. This is given as xi plus 1 is equal to xi minus 1 by m. yi plus 1 is equal to yi minus 1. Many times it is not necessary to compute the x-intersections for scanline with every polygon side. We need to consider only the polygon sides with endpoints straddling the current scanline. It will be easier to identify which polygon sides should be tested for x-intersection if we first sort the sides in order of their maximum y value. Once the sides are sorted, we can process the scan files from the top of the polygon to its bottom, producing an active edge list for each scan line crossing the polygon boundaries. The active edge list for a scan line consider all the edges crossed by that scan line. In summary, a scanline algorithm for filling polygon begins by ordering the polygon sides on the largest y value. It begins with the largest y value and scans down the polygon. Scanline conversion algorithm for polygon filling. In this video, we are going to see about scanline conversion algorithm for polygon filling. Read n, the number of vertices of polygon. Read x and y coordinates of all vertices in array x of n and y of n. Find y minimum and y maximum. Store the initial x value x1, y values y1 and y2 for two endpoints and x increment del x from scanline to scanline for each edge in the array edges n cross 4. While doing this, check that y1 greater than y2. If not, interchange y1 and y2 and corresponding x1 and x2 so that for each edge y1 represents its maximum y coordinate and y2 represents its minimum y coordinate. Sort the rows of array edges of n cross 4 in descending order of y1, descending order of y2 and ascending order of x2. Set y is equal to y max. Find the active edges and update active edge list. If y greater than y2 and y lesser than or equal to y1, edge is active, else edge is not active. Compute the x-intersects for all active edges for current y value. Initially, x-intersect is x1 and x-intersects for successive y values can be given as xi plus 1 implies xi plus del x, where del x is equal to minus 1 by m and m is equal to y2 minus y1 by x2 minus x1, that is slope of line segment. If x-intersect is vertex, that is x intersect is equal to x1 and y is equal to y1. Then apply vertex test to check whether to consider one intersect or two intersects. Store all x intersects in the x intersect array. Sort x intersect array in the ascending order. Extract pairs of intersects from the sorted x intersect array. Pass pairs of x values to line drawing routine to draw corresponding line segments. Set y is equal to y minus 1. Repeat steps 7 through 13 until y greater than or equal to y minimum. Stop. In step 7, we have been checked for y lesser than or equal to y1. Hence, step 9 becomes redundant.